Okay, good morning to everyone. Welcome to our Scalar webinar, and thank you for your interest in joining us today. We will be presenting you the work we did in synergies identification and the potential assessment. Just to give you a brief context, this project, we target the process industry, which is one of the main pillars of Europe's economy. This industry is energy and resource intensive with significant carbon emissions and a high dependence on resource availability. Industrial symbiosis is a solution to close the loop, and therefore the origin of this project. We'll give you just some brief words about the project. Scalar, the Scaling European Resources with Industrial Symbiosis, is a Horizon 2020 project helping industries increase efficiency through resource sharing. The goal of Scalar is to provide mechanisms to accelerate the journey towards efficient and quick implementation of industrial symbiosis in the European process industry. We did this by developing action plans and adapted solutions to industrial stakeholders and communities. We worked closely with a wide range of stakeholders, including industrial networks, consultancies, researchers, and policy makers at various geographic and political levels to deliver practical tools and guidelines for industry actors engaging in resource efficiency, reuse, and sharing. Scalar, we have a consortium of 5 partners. We have ISQ, the coordinating institution where I am from. I forgot to tell, my name is Marco Estrela, I'm the coordinator of the project. Then we have Climate Kick, Stran Innovation, Quantish, and the University of Cambridge. Today's objective is to give you some highlights on how did we assess the European Union potential for industrial symbiosis. Our agenda for today, so we start by giving you a contextualization of the work, followed by some highlights on how we use how the methodology we used to assess the synergies, and we will end by showing you some of the main results, namely the mapping activities and the most promising synergies. In terms of context, well, one of the objectives of the project was to list the 100 synergies, and we start this by well, from a wider range of synergies, more than 1,000, then we shortlisted this to 100. And for these 100 synergies, we looked at the procedures and the technologies that make them possible. And then, following this, we did economic, technical, and environmental assessment of these 100 synergies. After this assessment, we shortlisted these 100 synergies to the 38 most promising ones. And we ended by doing an assessment of the industrial symbiosis potential at EU level. So I will give the floor now to my colleague Jean-Baptiste Quintana from Stran. But just before that, please, if you have some questions, you can use the chat and write them, and then in the end we will try to answer them. Thank you. Now, Jean-Baptiste.
Good morning, everybody. I hope everybody is hearing me well. So I will present you my part on how to find a synergy, because it was the first step of the project to establish the list of 100 synergies. So we developed a proper methodology to identify this sample of synergy. First, a short reminder on the synergy creation process. So when you want to create a collaboration between industries and share resource, material and energy, for example, between industries, you have a process like this. So you need to identify opportunities on site. So you can use some tools to identify this type of opportunities like LESTS, SWOT, MFCA, or value mapping. Once you identify the opportunities, you need to identify a synergy, and this step which is crucial to start an IS project. After, you need to assess the synergy in detail, implement the synergy, and operate the synergy. But for that step, for the synergy identification, tools and methods exist to support you on finding synergies. So I will start to introduce some tools and methods you can use. Some tools are dedicated to are matchmaking tools, so they help you to identify a matching between the resource you want to you have and the potential receiver for the resource. You have also mutualization platforms and substitution platforms. I had here a full list of tools that exist and can help you to identify synergy and create synergy. Sorry. We have also databases and knowledge repository you can use. So, for example, the list of 100 synergies we identified in Scalar. I will present it after. Also, the Scalar shortlist of 38 most impactful synergies. You have also the Maestri library of case study, which is a result of another European project on industrial symbiosis. You can also see and study the IS case study that are in papers. So, for example, Kallenborg case, Bussy case, and Taranto case. They are already operating synergies, and it's very relevant and useful to see to have a feedback on the experimentations and the synergy already in place. You can also go and see the IS data toolbox and some academic papers. You can have the help of intermediaries, for example, knowledge brokers or coordinating bodies. It's now famous, but the National Industrial Symbiosis Program did a lot to help the identification of synergy and the implementation of synergy all around Europe. And you can also use some consultancy body. But in our so if you're a local authority, you have some tools like it's just an example, but you can of course find other tools, but it's a short list to explain you what is the best tool depending on your position. So if you're a local authority, you have Active, which is very interesting, but it's mainly developed in France. Inex Circular, B-Circle, Reciter, and Sharebox, which is ongoing development. For industrial park managers, you have Reciter and Phoenix, who are very efficient to find potential synergy in clusters. B-Circle is also developed to help industrial managers. For waste manager, Upcycler provide services in waste management, so it's relevant to use this. And for process industries, like we target in Scalar, Phoenix is useful. The EPOS toolbox is the result of another project dedicated to IS, B-Circle also, and Sharebox, which are also on development. So in our objective to find 100 relevant and promising synergies, Scalar, with the Scalar project, we developed our own methodology and identification tool. So the objective was to develop and reuse a reusable methodology to identify synergy. This methodology, for this methodology, it was really important to be able to identify existing synergy, but also innovative and new synergies. And with that methodology, we identify 100 synergy and we used this result to quantify the European potential for these 100 synergies. This methodology is based on a systemic approach, so we consider the productive system, a process like a productive system, and you have so all input flows and that are defined as input of the system, and output flow, emissions, waste that are considered as the output of the system. The principle, so the methodology is based on resource matchmaking. Once all input and output stream of an industrial process are identified, we deep characterize the resource, the composition, and also the properties of the resource. And with some matching algorithm applied on resource names and chemical composition, we succeed to identify synergies based on the ontology and the name of the resource, but also on the chemical composition and fraction of resource. So this is really useful to find both direct and indirect synergy that will present ISQ after. So the result of this synergy identification step is a list of 100 varied and promising synergies. So, and the 100 list is based on best practices, on industrial cases, but also existing synergies and innovative synergies. And all of these synergy were identified thanks to our methodology I presented to you just before. If you want more details about the synergy identified, you have a dedicated report and a dedicated guide for which you have specific sheets for each synergy. So here you can have an overview of Sankey diagram for all emitting sector. It's a number of synergy, not the volume, but in number of synergy, you have the emitting sector and the receiving sector for all the synergy we identified in Scalar. So I will let the talk to my colleague João from ISQ, and he will present the technical assessment of the synergy and the amazing work they did with their technology database.
Good morning, everyone. Okay, good morning, everyone. Thank you, Jean-Baptiste. My name is João Azevedo. I'm from ISQ, and I will introduce you on the methodology and the procedures that we use to technical assess of these 100 synergies. So once we have identified the 100 synergies to study and going deep on the project, it was necessary to create a structure that will define the different variables that are associated to those synergies. The main goal was to characterize and assess its technical viability in order to continue our study. The methodology we use, we define it as a technology database. This technology database was created from the basis in a closed structure that will allow not only to characterize these 100 synergies, but as well to compile information that will allow to support the following environmental and socio-economic analysis. So first of all, I would like to introduce a concept that have been used in the Scalar project on this technical part, and it starts from the division on two main type of synergies. We consider that these two are divided in direct synergy types and indirect synergy types. Direct synergy types, as the name introduces, are those synergies that connect an industry site A to an industry site B, where the material will be used, and this process will pretty much consider the transportation and the logistics. Why? because mostly we are using directly the raw material, the byproducts or the residues and waste that we have from an industry directly to another one without the need of intermediary process, treatments or pre-treatments. As can be thought, that these processes will require less transformations, less cost analysis required to canalize it to another industry. From the 100 synergies analyzed, 48 direct synergies were contemplated in this process. Regarding the indirect synergies, as you can see here in the picture, once we have the surplus or waste from one industry, sometimes we require intermediary processes in order to make it feasible to be used by another industry. In this case, of course, more transformation processes will be required in between, and a most deep cost analysis is required as well. So this concept was the basis on the division of our technology database and the procedure that I will present now. Just to quick reminder, from the 100 synergies, 52 were identified as indirect synergies with higher requirements. So the first step that we done here on the technology database definition, we divided on three main blocks of information. So first of all, we need to categorize this synergies typology structure, and we create the first block of synergy characterization. The main objective was to make it clear to each synergy which was the byproduct, the state of matter involved, which was the element of interest that sometimes is associated to the surplus that we are considering. We define the sender sector and process, as well as the receiving sector and processes. Later on, we found out that was really interesting and necessary to make a deeper synergy description. As you can see here, all details on the synergy that could get in the process were presented here in this cell. Later on, we define as well which is the technical objective of the synergy. We define if this was a resource exchange, energy, material, or water, and so on. We define the type of synergy, if it was direct and indirect, and of course, the identification source that was associated. If it was, as my colleague Jean-Baptiste introduced, mostly we define if this was an innovative synergy or if it was an already implemented synergy. So this stage 0 pretty much compile all the contextualization of the synergy to be analyzed. Later on, we step into the stage 1. In this stage, the objective was to characterize the procedures and understand that as procedure, we define that the procedure will consider all the actions that are needed from the production of this surplus until the end on its utilization. Okay, so pretty much what we have identified, if it was a direct or indirect synergy, there will be a requirement on intermediary processes or not. We define the procedure by qualitative assessment, where we define the name of the procedure, and we compile all the necessary steps that are detailed for each one of the synergy. Later on, we define as well which are the technologies in the case that this procedure consider one, and we define this by its name and a general description of what is involved with it. We also find out if it was necessary any kind of post-treatment and of course its description for a better understanding. In case that was necessary some complementary information to support the understanding of the full procedure and technology, it was also introduced in the database. Later on, we move to the characterization of the synergy with the different more technical approaches. First of all, we identify if this synergy has a procedure or also a technology involved. We define if it was made at site or an external facility or just in the receiver. We also look for the yield and the productivity, as well as the recovery rates of each of these procedures and technologies in case of associated technologies, and we define this on the basis on the technical reference that were available during our research. Later on, we move to the characterization of the transportation, not only by defining if it was a required transportation or not, but also defining the means of transport that are associated to this synergy, and also the description. This general information that we define on stage number 1 allow us to compile all the generic techniques, technologies, and logistics for each synergy type. Once we have characterized this second stage, we move on to the final technical characterization of the synergy. The objective was, of course, as we know, is very important to sustain the synergy implementation, this economic context. So we make an estimation on the expected investments and costs, as well as the inputs and outputs associated mostly to the technologies and the procedures involved. In general, we define, first of all, which are the key costs associated to the synergy in a more overall perspective, just to the readers to have a better understanding on if they have to focus mostly on the procedure or on the transportation regarding costs. Later on, we move to several variables that were defined to characterize the inputs. So we consider if there was heat demands, if there was any electricity demand, water demand, and other necessary products associated to this technology and procedure. Later on, we move to the economic characterization, where pretty much we look for the operational costs and capital costs associated. In case that we didn't found, we look at other complementary information that can sustain this economic characterization, like the return of investment, payback period, and useful life. Of course, there is some information that was required, mostly qualitative, to support this economic characterization, where we compile all the information available from the different sources that could sustain and somehow make it an easy, understandable topic, the fact that economics are and have to be dealt with careful. So we try to complement this with this qualitative information. Mostly the outputs that were considered for each one of the synergies were regarding the CO2 emissions, the residues involved, and other relevant products that were found to be associated to each one of the synergy. So this process was pretty much made for the 100 synergies. Was an extensive work that resulted in a complete technology database that has this information compiled in the same structure and is available in one of our deliverables from the project for consultation. So I think this is a very important question that probably our listeners are having at the moment. But where to obtain this information to make this full characterization of a synergy in all these variables? Pretty much we were looking for the best reference documents on the best available technologies, the BREFs that are available by the European Commission for most of the industrial and industrial activities. This was a big source of information, but sometimes we have let's say the constraint that these BREF documents were somehow obsolete, so that in case that they were not actually in the current state more improved, we have to look for other sources of information. That way, we look for publications that are available, fully available regarding specific industrial process. We were looking as well to sectorial books regarding each one of the synergies, the catalogs, and of course, industry consultation and expert knowledge on the topic. Fortunately, from the consortium, we have different industries involved with us and could access to some of this information. This process of gathering information is very important and should be done carefully. It maybe can require some dedicated time, but the results are absolutely necessary to support this technical implementation of these synergies. Once we have made this full characterization of the pre-presented variables, we look for a final decision on the technical viability analysis. So pretty much we evaluate if the technology was available in the market from the previous information sources. Later on, we analyze if the technology is already implemented at large-scale industries. Okay, and we complement this with the logistic, economic, and economic analysis that I previously present. So the final conclusions were supported as well for more qualitative comments to support this decision, but pretty much the results on the technical feasibility of each one of the synergies were presented in this scale that we have here in the green table. So pretty much the synergy technical feasibility was evaluated at feasible or not feasible, but we define different levels of feasibility or unfeasibility for them. In the case of the feasible, we have defined some of them as feasible with low technical requirements, another ones with high technical requirements, and another ones that were feasible with limited potential. I'm not going deep on the description of each one as it is available on our deliverables, and I invite you to look for it. It's a very interesting work, a very extensive review on all these 100 synergies, and we think that this information is the starting point for a larger scale implementation on the technical side. Regarding the not feasibility or the unfeasibility of the synergies, we divided in two. The ones that are not feasible because we don't have available support data, and another ones that are associated to underdeveloped technologies that pretty much were on the lab scale, on the prototype level. So in this regard, we could assess and decide and define if the synergies were really technical, viable to go on the process and analysis to reach the final objective that was to evaluate the synergies potential at the European Union scale. Okay, so thank you very much. I will let my colleague Lindsay to step into the environmental assessment. Thank you very much.
Okay. Hello, everyone. So I'll be presenting the environmental assessment work that was done by Qantas. And we used the life cycle assessment methodology. The following indicators were used to evaluate the environmental assessment. So climate change, impacts on human health, ecosystem quality, resources, and withdrawal. And the functional unit, so this is the unit for which environmental impacts are calculated, are for a waste stream to be sent to a receiving industry over a 1-year period. So this is an example of the different synergy types that were evaluated. The objectives of the environmental assessment were firstly to quantify the environmental impacts or benefits of the 100 synergy types that were described at the beginning by Jean-Baptiste from Stran, and then to benchmark these different synergy types against a defined baseline scenario, and then finally to provide input for the social and economic assessment. So if we consider a baseline scenario as no exchange between two sites. For example, site A may produce a waste or byproduct, and site B might need a certain raw material or fuel, but there is no exchange between these two sites. This is our baseline scenario. The synergy scenario is where there is exchange between these two sites, where the waste or byproduct from site A is then used as a raw material or fuel for site B. And going from site A to site B, there might be transport, or there might be a certain procedure or technology that needs to be done before being appropriate for site B, which is what João just described in the previous slides. So if we consider the baseline scenario, usually we have a waste treatment. It could be landfill or incineration, and this is shown by the gray bar. It has a certain burden or a certain impact on the environment. And if we consider now the synergy scenario, we might have additional impacts related to transport or procedure, but we also have an avoided impact because we don't need to purchase a virgin or a new raw material because we are using a waste now as a raw material. So this generates an avoided impact or a benefit on the environment. We considered direct synergies to have no procedure and indirect synergies to have a procedure, as João mentioned in the previous section. What we did for the environmental assessment was more of a screening life cycle assessment, which doesn't consider transport or procedure, although we did look at certain procedures that were identified as potentially being energy intensive to see what the impact could be on the environmental assessment. And so to summarize, for each of the indicators, we calculated potential savings, which is the second column, but these are presented or converted into benchmarks that might have more meaning. So what these numbers mean are, for example, for climate change, if the 100 synergy types that were evaluated were scaled up and put in place across all of Europe, the savings generated would be equivalent to about 29 million cars not driven, or taking 29 million cars off the road. In terms of human health, this would be equivalent to 6.6 billion cigarettes not being smoked. For ecosystem quality, this would be equivalent to 3.6 million hectares of forest saved from conversion to concrete. In terms of resources, 350 million barrels of oil not extracted, and in terms of water withdrawal, 1.1 million Olympic-size swimming pools. So what we can conclude from this environmental assessment, the key learnings here are that industrial symbiosis is a key driver to leverage the circular economy in Europe. And a few other points. There was a large-scale lack of data on waste stream volumes, so some of the potential was difficult to evaluate. We saw that the most unexploited potential was in the receiving sector of glass and ceramic, and in the sender sector of steel. Sectors which appear to be the most advanced in terms of industrial symbiosis are cement and steel, and intermediaries play an important role in encouraging industrial symbiosis. Not surprisingly, compared to direct synergies, indirect synergies are those for which the potential remains still largely unexploited. So these were the key learnings for the environmental assessment, but a lot of them hold also for the socio-economic assessment, which will now be presented by Jean-Baptiste from Strane.
Thank you very much, Lindsay. So yes, I will present you now the socio-economic assessment. Which is a methodology developed during this project, and we also reused a lot of results from the environmental assessment. So in the same mindset, we compared the baseline scenario with a synergy scenario. So a baseline scenario with industry A and B totally working separately. And so the initial scenario was a waste or byproduct generated by the industry A, which is sent to landfill and incineration, and an initial scenario for the industry B, who buy raw material that are extracted from the land and use energy like fuel fossil fuel, heat, and electricity consumption from carbonated energy. And we compare it with a synergy scenario for which we consider procedure or not, depending if it's direct or indirect synergies. So if we see at a synergy level, the approach we retain and the values we assessed are this one. So the methodology is based on the increase of the resource intrinsic value added. So we consider that the waste does not have any value, intrinsic value, because it's a cost for the industry A, and it's sent to waste management solution, which is generally landfill or incineration. Convert this waste in a new resource, a second life resource, will increase the resource intrinsic value. So we calculate all associated avoided costs, like avoided landfilling costs, avoided incineration costs. We also calculated all tax avoided, like landfilling tax and incineration tax, carbon tax avoided, and also the job creation for the system. Sorry for the noise. We also reused the results from the environmental assessment, and we used the LCA indicators on human health and the environmental avoided impacts, and we converted them in economic values. So it was interesting to compare the economic values generated by the avoided impacts on the environment and the human health. We also try to quantify the investment cost and operational expenditure when it was identified in the technical assessment step. So the results at the beginning, we try for the technology and synergies for which we had enough information on the capex and opex. We identified the total investment in Europe. We identified the opex each year to operate the synergy and run the equipment. We calculated the value added generated by the intrinsic value increase of the material. We also calculate the VAT associated, and we made a link between the value added and the direct job creation. Depending on the direct job creation, we estimated the indirect job creation, and we compared all the economic values in the previous step with the environmental and the human health benefits that we converted it in economic values, and we compare it with the real monetary values. We also calculated the waste management cost and all taxes, depending the scenario, incineration or landfill. So at the end, we have a lot of value added generated by the synergies, so 33 billion euros of value added, and a potential of the 100 synergy around 350,000 jobs. And so that's very interesting for the. It's a first assessment, and we were deep in the assessment later in the project. So sorry, and you have at the right you have also the deliverable where it's explained all the methodology and the results that we will share with you the link at the end of the presentation. Sorry. So at the end, all the previous steps, so the identification of 100 synergies, the environmental assessment, the technical assessment, and the socio-economic assessment aimed at identifying the highest potential in Europe. So it was important to map the potential, because once we have the potential, theoretical potential with all the resource exchange, it does not mean that you can really implement the synergy considering the distance, for example, between the sites. So we performed some mapping activities, and we mapped around 6,600 industrial facilities in Europe on 17 sectors and 84 activity segmentation. So when we talk about the sector, it's like steel, cement, organic chemical, inorganic chemical, non-ferrous metal, and so we had agro industries. So we had 17 sectors like this. And for activity segmentation, it's like, for example, in organic chemical, you have the lower olefin production, and that's what we call the activity segmentation. So just an overview of the sector distribution in Europe for process industries. And you can see here that all the sector we mapped are related to process industries and continuous industries. So agro-industry, fertilizer, cement, ceramic, large combustion plant, glass, inorganic and organic chemical, non-ferrous metal, paper, pharmaceutical, refineries, slaughterhouses, steel, textile, waste incineration, and wastewater treatment plants. So here you can see the distribution of the sites all around Europe. So it was a massive work of data collection and data merging, and we succeed to create a map of major location of process industries in Europe that you can see here. And with this map, we succeed to identify geolocated synergies. So with one synergy of the 100, for example, we were able to identify all combinations between all the sites involved in the one synergy. For just another analysis, to identify the best IS location, so the best industrial symbiosis location. So here you can read a map with the density of large environmentally impactful industries in Europe, and we identified 10 hotspots with 4 major hotspots that mean between 100 and 120 sites per 100 kilometer. So you have here the UK Midlands as a major hotspots, the Benelux region, with also the east, the west of Germany and the northeast of France. You have also the north of Italy as a major hotspot, and also the northeast of Spain with the Catalonia and Valencia region. Other medium hotspots are in Ile-de-France and north of France, the western coast of Portugal, the Madrid region, the Lyon region with the Chemical Valley, the Krakow region, and the east of Germany and Prague region. So it does not mean that there is no potential not in the hot regions, but in this region you have a large, very good possibility to identify a partner to implement a synergy. So here is just an overview of the hotspots. It's just an overview of the hotspots and the distribution of the sites. So, for example, we can you can have the details of the distribution in the deliverables, but here you can see, for example, that you have a lot of brick and roof tiles manufacturing in northeast of Spain. We have also other key figures like this, but what is really interesting is to see the best location for IS is where you have for the cross-sectorial IS implementation is where you have a wide variety of sites. So that's interesting to have this analysis and see where are the best location for the synergy implementation. We also developed several other maps, so general map, including also other industry like metal treatment industries. So not only process industries, we also have wastewater treatment plants with the major plants in Europe. So not all the plants, but the plants with the highest capacity in Europe. We develop a livestock farming map, mining and carrying operation maps, and we also made several analyses on the industrial installation location, and if they are located on cities or on functional urban area, to see whether or not major industries are in high density population area or low density population area. We also made a district heating assessment with the distance between the heat emitting sites and the downtown centers. At the end of the aim of this mapping was to identify all potential combination in Europe, and we shortlisted 38 most promising synergy because the 38 most promising synergies represented 90% of the environmental and socio-economic impact of the 100 synergies. So that is why we made a geographical analysis of these synergies. It concerned 327 million tons of material, and you have more than 1 million combination in Europe. So 1 million couple of sites that could create a collaboration and a partnership to exchange the resource. You have the full result of the 38 most impactful synergy with the description of the synergy in a sectorial outlook guidelines. With these 48 most impacting synergies, if these 48 synergies were totally implemented, so 100% of the 38 synergies totally implemented in Europe, we would have around 22 billions of added value, 5 billions of value-added tax, around 2,000 jobs, new jobs in Europe, 200,000 new jobs in Europe, more than 100,000 new indirect jobs in Europe, and other massive benefits like waste treatment cost savings and 2.5 billion meters meter cube of water saving, and 42 billion of equivalent damages cost avoided on the environment and on the human health. And now we compare the full potential with the current level of implementation of these 38 synergies. And for these 38 synergies, which include a lot of existing synergies, but also new and innovative synergies, we see that the potential is not totally exploited for the moment, and we are still around 1 billion of added value to reach, 1.7 billion of value-added tax to reach, more than 85,000 new direct jobs, 42,000 of new indirect jobs, and other the benefits of waste treatment cost saving and water saving are also huge. So it was really to see whether or not the synergies are fully implemented or not. And for the sample of 38 most impacting synergy, we see that for the moment the potential is not fully achieved, and even for synergy that are really have a high level of implementation, we have still a potential to achieve. So I will let Marco explain about the reports and where we can find the reports and the guidelines of the project.
Okay, Well, we reached the end of the presentation for today. As I said in the beginning, you can ask us some questions using the chat tool. Meanwhile, I just want to show you where to find some of our work. So you can download all the reports from our website. You have here the link. And these reports give you a lot of information and detailed information about what we did in the project, the different areas. We also did some quick guidelines and some guidelines for industrial symbiosis, which provide you in a synthetic way a lot of information for people that would like to start implementing projects, industrial symbiosis projects. And of course, you can visit our website to find more information. I take also this opportunity to inform you that, I don't know if you are all aware of this, that today we will have another webinar that will be held by our colleagues from the University of Cambridge. It will start at 14 CET. And you have on the website the link also to register to this webinar if you are interested. Also, in the end of the month of October, 27th of October, we will have a final event of the project, which will be finishing in end of October, the scaling the circular economy for industry event. It will take place in the afternoon of 27th of October. So you will be able also to attend this if you would like. So I don't know if there is some questions already on the chat. At least I don't see any. Of course, you can also contact us if you would like after the event. So I don't see any questions for now. Okay, so if you don't have any questions, well, I would like only to thank you for your presence in this webinar, and feel free to contact us. You have the contacts if you have later questions, or if you want to know more detailed information about what we presented today. So thank you, everyone, and bye-bye. And we have today another webinar, and end of October we will have our final event where we will be presenting more information, and we will also be having some external speakers that will give us some interesting presentations for sure. Thank you. Bye-bye.
Thank you, everyone. Bye.
Thank you, everyone. Bye-bye.
Thank you.
Everyone, next time. Thank you.
Escolhe.